Hi, good day. My name is William T. Dongo, your professor for today. Today we will be discussing about low pressure, low viscosity duct system design consideration for commercial, and then we're gonna be referencing with the manual cue. Okay. Uh, the lecture that we're gonna have today will be about section 3. Basic. Actually, it's about the basic on the air conditioning, but I'll call this as a basic engineering because it might involve a little bit terminology about fluid dynamics. We're gonna discuss about airflow, pressure, velocity, and temperature inside the duct system of the heating, ventilating, and air conditioning system. The first one we'll be talking about will be flow and pressure equation. First one we got under that thing, we're gonna talk about sensible heat, total pressure equation, total velocity equation, duct flow equation. And then below that, the duct pressure measurement units that we be using in the AC duct system will be inches of water gauges, inches of water column. And then inside there, we're gonna do a duct pressure measurement. I'm gonna show you how to take the static pressure, velocity pressure, and then the total pressure. And then we're gonna talk about the friction regain conversion, effect of friction in duct pressure, effect of friction on regain and conversion, pressure measurement, fan performance curve, and then duct system curve. Then we're gonna go on top over here, we got the sensible heat. Okay, in order to get the CFM of the particular system, we're gonna determine the CFM, the capacity of the pump that we're gonna, the capacity of the fan that we're gonna use. In order to get that, you must first determine how much CFM we need inside that room. For the cooling load, for calculating the CFM, we're gonna have the first get the sensible cooling load, which is in BTU divided by 1.1 times room dry valve plus supply dry valve. And then for heating, we get CFM is equals to the heating load, which is in BTU divided by 1.1 times the supply dry valve, and then room CFM, room dry valve. So in those two equations, you can determine the amount of CFM you need, and then you go to the fan specification to dictate what type of fan you're gonna use inside for that particular system. And then on the duct, we're gonna talk about total pressure equation. The total pressure equation is equals to PT equals to PS plus PB, in which pressure total is equals to pressure static plus pressure velocity. And how we derive onto this one, I make a simple diagram here as the static pressure and the velocity pressure and the total pressure are in relation inside the duct. I got here the black color in the diagram. It's just like it's spread all over. You got SP, 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 which are in the black. That means the SP is static pressure. It's hitting right on the duct. In this duct right here, the part of the duct. It's a pressure inside there. And then we got the velocity pressure. And then the velocity pressure is the pressure inside the duct in here while the air is moving. And then you add the two, SP plus velocity pressure, which is equals to total pressure, which is the red one I got in here. So in here, you got total pressure is equals to velocity pressure plus static pressure. Okay, total pressure equation is equals to total pressure is equals to static pressure plus velocity pressure. And then now I'll show you how you're gonna get the static pressure first inside the duct. In order to get that static pressure reading, you gotta use a manometer. Manometer with a pitot tube. This is the way it looks like, how you gonna get it, okay? You got the pitot tube right here. You got your manometer here. What you gotta do, you gotta drill a hole on the skin of the tube, or of the duct, and then you plug the pitot tube on the manometer, and then you take one leg of the duct, of the pitot tube, stick it right in the skin of the duct, and then you take the reading on the manometer, and then that's your static pressure. Now let's talk about the total pressure. In order to get the total pressure, this is how you're gonna hook it up. You're gonna drill a hole to the duct, hook up the pitot tube on the manometer, and then stick the end of the pitot tube inside the duct. You put it right in the middle of the duct, going to the stream, against to the stream of the airflow. And then the reading you have on the manometer, and then that will be your total pressure. In order to get your velocity pressure, this is how you're gonna hook it up. To get the velocity pressure, you drill 2 holes and then hook up the 2 pitot tube on the manometer. One leg of the manometer, one of the pitot tube, you gotta put it on the skin of the duct where you drill a hole. Right there at the skin, but make sure it's inside the duct. And then the other end, you put it inside the hole, and then it's right there. Put it in the middle. So the reading that you're gonna have will be a total pressure. Okay? And then that's your total pressure. Okay. So the one we're gonna get now is the velocity. Velocity pressure right here is equals to 4,005 times the square root of pressure velocity, and then the unit is equals feet per minute. And then PV is equals to velocity divided by 4,005 to the square. Okay? PV is equals to velocity divided by 4,005 to the square. And then to get the CFM, cubic feet per minute, is equals to velocity feet per minute times area to the which is square feet, and then you gotta have here is CFM. You gotta be cubic feet per minute. Okay. So we discussed how you're gonna take the readings on this one right here. Okay. Energy supplied to the fan motor, then for transfer this energy to the air in the duct. Spring energy is represented by static pressure in the duct. I showed you how to take that. Kinetic energy is represented by the velocity pressure of the air flowing through the duct. The total energy of the air stream is equals to spring pressure plus kinetic energy. And then the other one is that I showed you already how to take the readings on those. Now, that means that any point along the duct, the total pressure must be equal to the sum of the static pressure and velocity pressure. Okay, now we're gonna talk about frictionless regain and conversion. The average velocity decreases because there is no friction. What's that? The average velocity decreases. And because there's no friction, the corresponding increment of the velocity pressure is completely converted to static pressure. Static regain. Static regain is the increment of velocity pressure that was converted to static pressure, is called the static regain. Effect of friction on the duct pressure. Friction dissipates the energy in the airstream. In the duct system, to continuously decrease in the direction of the airflow, okay, then friction causes a continuous reduction of total pressure in the direction of the flow. What we're talking about, the pressure regain and things, it is, I made a diagram of a pipe in here, a duct in here, in which we got the duct, and then it goes down to small diameter duct, and then it goes back here. Go back to the normal duct. Velocity decreases, okay? Velocity decreases in conversion to static pressure. On this side right here, in here the velocity, and then when it reaches, it decreases, and then the static pressure increases. The way it is over here you got a normal size diameter, and then in here you see the static pressure. And then we went to the restriction here, the static pressure went down. But the velocity pressure increases on this diagram here. This is the baseline, and then here the velocity pressure is right here. And then the static pressure, velocity pressure went up as it goes to the restriction. And then the same thing, it went back, it went down to normal once it passed this restriction here. Okay? So when you got the friction, it goes to the restriction, then the static pressure decreases and velocity pressure increases. It makes sense to that. The velocity pressure increases, and then the static pressure decreases, as it shows in here on the graph. Okay? Effect of the friction on regain and conversion. This is what I explained. The effect of the friction. Because over here you're going to get a lot more friction there. When air moves through the duct, the total pressure always decreases in the direction of the flow. So there's always a friction going through the duct. And it decreases the total pressure. The static pressure can increase or decrease depending upon the changes in the velocity that occur at the transition, branch and tees. Abrupt changes in the section area are very inefficient. Sometimes little or no regains occurs, and most or more or all the velocity pressure is lost. Okay. Now we're going to talk about performance curve. So we determine the CFM on what we need to the duct system by calculating the amount of CFM we need, and then once we know how much CFM we need, then we deducted all those losses, just like the friction losses that we have, the equipment that we have, and then after that we're gonna have the performance. Then we select the fan, and then on the fan performance curve, you got the typical, the curve that each fan will have a curve, characteristic a curve that will indicate for certain speed it at a certain CFM. Okay? The performance curve, the CFM that is delivered by a fan, will depend upon the resistance it is working against. This resistance is provided by the duct run, fittings, and by any device or components that are installed in the airflow path. Okay? Total fan curve, and then the speed change. The total fan curve is only necessary appropriate how fan pressure in inches of water is related to fan flow rate, CFM.